Welcome back. Today we are going to start our discussion in Unit 3. First topic we're going to look at is the topic of the mole. Now the mole is very important to chemists, not because it's a little animal that buries in the ground and causes all sorts of havoc in your lawn, but because we're going to use it as a unit. Now remember, in chemistry, a lot of times we're working with atoms. Well, atoms are hard to see. We can't really count atoms because you can't see them. So we're going to use this idea of the mole to take atoms and make them a little bit more concrete. So why we use the mole is we use it to relate atoms to mass. Now mass is something that we can find in the lab where atoms really aren't. But through the mole we can actually calculate and determine the number of atoms. So if you are holding in your hand 3 grams of gold, you could actually calculate how many atoms you have. And we're going to do this by using the mole. So the mole is just an SI unit for an amount of substance. And we are going to use it in several different conversion factors to help us get to atoms from mass or vice versa, going the opposite direction. So Avogadro, this is a gentleman that studied chemistry, of course, and he looked at all these different ways to kind of relate, or the relationships between atoms and the mass of a substance. So he took an isotope of an element and started testing it, and what can we come up with, how many atoms are there based on these different amounts that he would have. And he came to the conclusion that in a substance, or in 1 mole of a substance, we have 6.02 times 10 to the 23rd particles. Now that's a really big number. If you write it out, so do your scientific notation, you would see that you'd have 21 zeros after 6.02. If you had a mole of pennies and you wanted to see how many or how much money you actually had, do the math. Take this 6.02 times 10 to the 23rd, divide it by 100, and you would find out you are pretty rich. So a mole is a huge number of particles. So this 6.02. Of course, Avogadro gets the credit for determining this constant. This number is not going to change. This is the number that is in 1 mole of a substance. So let's look at this idea of relating mass to atoms. And we're going to do this through molar mass. Of course, molar mass, you get that mole in there. So all we're doing is basically taking the atomic masses of the periodic table and we're changing the unit. Atomic masses are usually like AMU, atomic mass unit. What we're going to do is make it a molar mass, so all we do is change the unit so it's grams per mole, or the number of grams in 1 mole. So to do this, we are going to look up the mass, so look up the atomic mass on the periodic table. So now may be a good time to take out your periodic tables. And you'll notice there's lots of decimal places after some of these numbers. So just to make it easier on ourselves, we're going to round it to a whole number. Now if you have a molecule compared to just an atom, you're going to have to look up the individual elements and then combine their masses. Now often in a molecular formula you have those subscripts. If you have a subscript, you have to multiply the mass by that subscript before we add them up. Now talking about it gets a little confusing, so let's look at an example. So let's look at the example BaNO32. To find the molar mass of this molecule, we are going to break it up into its individual parts. So we're going to pull out our periodic table and we are going to look up the atomic mass, which we are now going to call the molar mass, of each of these elements. So first we find Ba. We look it up and round the answer, and we get 137 grams per mole. We're going to do the same for N. So nitrogen is 14. However, in this formula, you're going to have to multiply that because we don't have just one nitrogen. This 2 here is going to go to oxygen and it's going to go to nitrogen. Now it only distributes through what's in the parentheses. It does not go to barium. So we have 2 nitrogens, so we're going to take 14 times 2, which will give us 28 grams per mole. Oxygen, we look it up and round it and we have 16. And we have 3 oxygens in the parentheses, but we have 2 of those 3 oxygens, I guess. So if you have multiple subscripts, we multiply those together. So in this case, 3 times 2, or we have 6 oxygen atoms. And 16 times 6 is 96 grams per mole. Now to find the molar mass of the compound, we are going to add these all together. So 137 plus 28 plus 96, and we get 261 grams per mole of barium nitrate. Now, why do we want to know the molar masses? Well, molar masses are going to come in handy when we want to change from grams to moles. By changing from grams to moles, then we can look at atoms. So you could actually say, if I have my 3 grams of gold, how many atoms do I have? So to do that, I have to convert it to moles. So we're going to go back to what you learned a couple years ago in dimensional analysis. Remember, dimensional analysis was basically just times a line, where what you start is what you are changing from and what you are going to. Now the unit you are changing from always goes on bottom, so this is always our from unit. What we are changing to always goes on top. That way, when we actually do the math, we are going to cancel out our froms and left with our 2's. So hopefully, if we're going from mass to moles, we cancel out mass. The only unit we have left is moles, so we've actually gone through that conversion. So remember, that's a little review on simple dimensional analysis. So we're just going to do that, but use the new ideas that we've discovered, which are, so far, the mole and molar mass. So in doing this, if I'm starting as my from unit mass, I'm going to times a line. In this case, it's an arrow so that I can fit them both on one page. So my times a line, my from unit's going to go on bottom. So the unit I'm starting with is grams. My 2 unit is going to go on top. So this is going to be moles. Now when I use my conversion factor of grams and moles, I need to put numbers in here. It's not going to do me any good if it's just a unit. So what we find is for grams, we are going to use those molar masses. So we just learned how to calculate a molar mass. So we are going to use that number in this part. So basically we're going to look it up. So any molar mass, you're going to have to look it up. Sometimes you have to add it up if it's for a molecule. Now the nice thing is, if this is a molar mass, this is grams per mole. So this number is going to be 1, and this is going to be always 1. This is a constant. So whenever we have moles, we are going to have 1 in front of it. Now if we were going the opposite direction, if we were starting with moles and going to mass, we're still going to use the same conversion factor. The only difference is you flip it upside down, because this is now your from and this becomes your to. So again, if you're going from goes on bottom. So I'm going to have my 1 mole. Again, it's 1 mole. That's not going to change. On top is going to be your molar mass. And of course that may change because that's going to be dependent upon the molecule you are using. So again, let's look at an example. So I wanted to determine how many moles of NH42SO4 are in 6.60 grams. So I need to figure out what is my from and what is my to. Where am I starting? Where am I heading? So in this case, 6.60 grams is going to be my from. That is what I am given. That's where I'm starting. That's where I'm going to, or that's what I want to change. My to in this case is going to be moles, so this is what I want to change to. So when I set up my conversion factor, this is the unit that's going to be on bottom. This is my unit that's going to be on top. This number just helps me start my problem. So I'm going to have 6.60 grams of NH4 to SO4. And I am going to times a line. Now on bottom of my line is going to be my from unit, not the number, just the unit. So I'm going to put grams on bottom. On top is going to be my to unit, so this is going to be moles. Now I need to fill in some numbers. Again, in front of moles we are always going to use 1. For grams we need to get the molar mass. So I have to go back to my molecule and I have to look it up and add it up. So N is 14. Well, I have this 2 on the outside, so we have to remember 2 goes to the H and 2 goes to the N, so I have 14 times 2. I'm going to add that to hydrogen, which is 1 times 4 times 2, or 1 times 8. And I'm going to add that to sulfur, which is 32, and add that to oxygen, which is 16 times 4. I add that all up and I get 132 grams. So that's what I'm going to put as my molar mass. Then it's just as easy as doing the math. So I would have 6.60 times 1, divide that by 132, and my answer is 0.05 moles of NH4 to SO4. So again, not too difficult. All we're doing is setting up conversion factors. We just have to make sure that we get grams and moles in the right positions. Now we keep talking about knowing the number of atoms, and we use Avogadro's number to know that we have 6.02 times 10 to the 23rd atoms in 1 mole. So we can use that as a conversion factor, so we can easily change from moles to atoms. So to do that, this is my from, so it's going to go on bottom, so I still have moles on bottom. This is my to, so pick whichever one you want. So let's say atoms on top. So now again, to be a conversion factor, I need some numbers. Well, I'm going to use Avogadro's number, 6.02 times 10 to the 23rd, because we know there's that many atoms in 1 mole, or that many molecules, or that many particles in 1 mole. So you can think of these as pieces. If we're talking about something, these are the pieces. How many parts do I have in 1 mole? If I'm going the other way, all I'm going to do is flip that conversion factor around, because my from and my to have now changed, but the numbers are the same. Cool thing about this one is you can see this is a constant. This we already talked about being a constant. So these numbers are never going to change. When you're going from moles to atoms or atoms back to moles, you don't even have to worry about what the substance is. So there's no looking up and adding up in this one. No matter what the substance is, if you're converting between these two things, the numbers are going to be exactly the same. It's just what you're starting with is going to change, which is going to give us a different answer. So let's look at an example. We want to know how many moles of silver are in 3.01 times 10 to the 23rd atoms of silver. We need to have our from. Where are we starting at? Well, in this case, we're starting with atoms, so this is my from. What am I changing to? I'm changing to moles, so this is my 2. So this is my number I'm going to start my problem with. So I have 3.01 times 10 to the 23rd atoms. And I am going to times my line. Now my from unit goes on bottom, so I put atoms on bottom. My 2 unit goes on top, so I'm going to put moles on top. And then I just need to, again, fill in numbers. In this case, moles is always 1. Atoms is always 6.02 times 10 to the 23rd. And then I'm going to do the math. So I have 3.01 times 10 to the 23rd. I'm going to divide it by 6.02 times 10 to the 23rd. And I'm going to get an answer of 0.5 moles of silver, which is Ag. Now, if you didn't get that answer, be careful how you are plugging it into your calculator. Remember, if we're plugging this in, this times 10, you may want to use that EE button on your calculator, because otherwise, when you get to the bottom, what your calculator often is going to do is it's going to give you this, and it's going to divide it by this. But then it's going to take that answer and multiply it by 10 to the 23rd. So often you will find that your times 10 part, or the exponent on the times 10, is going to be off from what it should be, and you're going to wonder why your answers aren't coming out correct. So remember, if you can, as you're using scientific notation, use that EE button. Now the last thing we're going to do is convert mass to atoms. So this is the fun part. This is where we actually get to see how many atoms we are holding in our hand. So we have the long way and then we have the shortcut. So let's look at the long way so that we can understand why we have the shortcut. We've looked at each of these conversions already. So we have done mass to moles and we have done moles to atoms. So if this is my from, this goes on bottom. So this is going to be my mass, or my molar mass. On top is going to be moles. Now remember, moles is always 1. Molar mass I have to look up on the periodic table. So that's going to change for every substance. But if I do it, my grams or my mass are going to cancel. So I am stuck with moles. Well, now if I'm in moles, this becomes my 2, or sorry, my from. This becomes my 2. So now since I'm here, this is going to go on bottom, and atoms is going to go on top. Moles is always 1. This is always 6.02 times 10 to the 23rd. So those are the 2 that we've looked at. Well, if you notice something in here, you have 1 mole here, and we have 1 mole here. Well, this is on top, this is on bottom, so they're going to cancel out every time we do this equation. So since this is a relationship in 1 mole, and this is a relationship in 1 mole, we can actually shorten that and combine it into 1 conversion factor instead of doing 2 conversion factors. So if this is our from, we're going to put the molar mass on bottom. This is our 2. We're going to use Avogadro's number on top. Now the reason, again, we can shorten this and we don't have to do the 2-step through the moles is because this relationship is the same, or they're both related to the same number. Now that may not play in a whole lot now, but as we get further along into other chapters, you're going to see that sometimes you have to do it the longer way. If we go back the other way, again, just flip your numbers over or your conversion factor over because your froms and your twos have changed. So let's look at one of these examples. So how many molecules are in 125 grams of copper 2 nitrate? So I'm going to start with my from. So this is what I'm changing from. This is what I am changing to. So we're still going to start it the same way, always looking for a from and a to. So my from is 125 grams of copper 2 nitrate. Now, since I'm using grams, I know on bottom I'm going to need a molar mass. So molar mass of copper 2 nitrate. So I'm running into a little problem here, is this is just a name. So we need to go back and we need to figure out what is this formula, because the formula is going to help us get to the molar mass. So we're going to look up copper. And we get Cu. Now we notice copper can be +1 or +2. So how do we know which copper we're using? Well, that comes from this. So remember, this tells us the charge. This tells us which one we're using. So we are using copper 2. And we are going to add it to nitrate. So we look up nitrate, it's NO3, it's -1. We need this neutral, so we know in the end we need 2 NO3s to make this a -2, which will then cancel with copper. So this becomes 125 grams of Cu NO3 2. Now we can times our line. This will allow us to get our grams on bottom. We're changing to molecules on top. In front of molecules is always our constant, 6.02 times 10 to the 23rd. Grams, we need to, again, look it up and add it up. So copper is 64. We're going to add that to nitrogen, which is 14. We have 2 of them, so 14 times 2. Add that to oxygen, which is 16 times 3 times 2, which is 6. So adding those up, we are going to get 188 grams. Now we are all set up. My grams will cancel. I'll be left with molecules. So I have 125 times 6.02 times 10 to the 23rd. Divide that by 188. And I get an answer of 4.00 times 10 to the 23rd molecules of Cu NO3 2.